All right, it says we're live. I am showing audio input. So let's see if we let's confirm. La la la. Okay, it's going by the microphone. It seems to be working. All right, I guess we're live again, everybody. Wow, I pulled a culture casino. How terribly embarrassing. All right, so let us continue. This should be our last little live stream because they're going to be closing a little over an hour. So, okay, let's share our screen one more time. All right, I think get that guy out of there. All right, don't mind my extreme anthropomorphization of different stuff. Okay, so, all right, I should probably do my little timer, which is the full. Oh God, how many songs did I go through? Time skip. Hold on. Here we go. All right, a little bit of ultimate battle to set the mood, and let us begin, my friends. All right, where are we? All right, don't need that guy. All right, we have our music and everything. All right, so what are we doing? All right, so let's set some variables. Number one. Okay, so some code. Let's just line in. All right, so let's set these things. All right, so I'm gonna do capital psi. I'll set that equal to a numerical count. Okay. Okay. Let me 7 point. I'm sorry, it automatically changes all these fonts and everything. Is that bold? That is bold. Hold on, let me undo the boldening. Plain. There we go. I'm gonna throw these in brackets just because I like to do that. It makes me feel safe. Or to have them and not need them, to need them and not have them. Okay. So, yes, I'd like to evaluate the input. Okay, we got that there. All right. So I'm going to do another input. So let's get our elementary length. I mean, this is crazy how close it is. Again, maybe just a coincidence. Maybe all these calculations are just bunk. Maybe none of this makes any sense. But it's, I don't know, if you able to notice enough different things, it's suspect, encouraging, engaging, under engaging. I don't know. Okay, elementary length. Okay, oh, just grab it from the code, derp. That's what we did for the other guy. Okay, so elementary length. Plop that down there. Okay, boom. Okay. Format, style. I know, styling and stuff. Oh, very entertaining. Yeah, let's keep them as non-bold. Or maybe we should just keep them as bold. I mean, it is bold, so alright, let's just. I'll save me. I know, I'm very indecisive. Bold. There we go. Alright, so I'm going to set that equal to our elementary length. Okay. You there. Alright. Meters. Alright. Smooth that to normal. Alright. Oh. Different little pieces. I'm like, no. Alright, that should be fine. Yep. Okay. Meters. Let's do the elementary time. Alright. Well, no, I don't think ever in my life I would have been so excited about defining unit bases. Jeez. Life is a highway. So they say. Oh no, that's elementary time, so we need time. Over here. Alright. Alright. Put you there. Okay. Oh. That there. Change this dude here. Plane. Alright. Elementary time. Yep. Alright. Oh. Seconds. Gotta have a reference to something, otherwise, what am I doing? Okay, and then the elementary energy. Alright, so that would be this term here. Let's express it in electron volts because that's how they have it expressed. Okay, put you there. V. Format. Face plane. Alright. Okay. So we've got our elementary units there. Cool. Yes, Dan, we're back. I'm back again. Guess who's back? Tell a friend. You don't have to tell anybody. It's just a quote from a song. Alright. So we got those elementary terms defined. Okay, so if we do, let's do this real quick. All right. Element. Why doesn't it have the bar over it? No, no, I want my. Okay. I have no idea why I didn't get the bar. All right. Evaluate. Okay, that many meters. All right. Let's get elementary time. All right, so elementary length divided by elementary time should give us, okay, approximately the speed of light. All right, because in dV we only get 4 significant digits, so after the 4th it's going to get a little wonky. Okay, so cool. Start to do some calculations here and see what they mean. Okay, save as. See, this is the thing that gets me. This is what always confused me. I would save these things. I have no idea what they are. Wolfram flux 7525. Let's go down 2. All right. Save. File. Save to cloud. All right, got that. Okay. I mean, the sheer fact that they were using a logarithmic basis to estimate this it's fantastic. I don't know, my two general postulates are math works and logs are useful. And we literally have the product log function up there to try to solve for this. Huh. Very interesting. Oh, so they're okay. I'm plugging one in for that, and then okay. Okay, so let's go to. Okay, divide our elements of the graph. Overall updates in the universe so far. Something events from the universe so far. Okay. All right. So the energy is much smaller. Yeah. Let's see. Let's go back down to maximum entanglement speed. All right. As to the maximum entanglement speed denoted by zeta, we may express this as 1 over t. So that would be, okay, so, oh, I totally missed those terms. I wasn't even looking. What a noob. All right, so now that we have this, it would be 1 over the elementary time, which should be, so let's put this here. Just evaluate that this works. All right. See, and then elementary energy. Oh, that was why it literally only got the E. That's above. Elementary energy divided by h bar. All right, so okay, yes. Do you not want to go to Wolfram Alpha? So, okay, let's code an H bar. We need to do that just because this is bothering me. Hold on. H bar should have all the digits for it. Should have 10 digits. It's at the 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so it ends at the 7 is that's where it's defined. Okay, joule seconds. All right, I'm sorry, that just kind of bothered me. All right, so let's throw in our elementary unit of action. Okay, so insert special character. Where are you? I know you're somewhere here. Oh, maybe you're not. Oh my god. I missed it, didn't I? Where are you? I don't see. Got psi. Wow. I'm so dumb. So let's do this. Enter. No, no. Oh, God. Oh, symbols, derp. Pi. There we go. H bar. All right. So input. All right. We're gonna. Where's H bar? We already have stuff. Okay. Let's just set that equal to its definition. So we can do some computation right here. Alright. No. Derp. Format. Show a face. Alright. Put that there. Okay. All right. That's set to its number. So let's do this again. All right. Let's actually throw H bar in. There we go. Go. Okay. It's before and center for free of the Wolfram language. Let me see. Okay, joule seconds is our. Oh, did I? Okay. Let's just see if this is going to do anything interesting. Okay, maybe I just need to click node. Nope. Traditional input format. Only input format. Oh. Okay, so I need to change my input format then. At least that's what that's saying. Let's go to output. That didn't help at all. Okay. Let's try this. Oh. Space. Oh, now it computes. Okay, apparently the touching the sides makes it get a little wonky because these are symbols. And then the okay. Okay, so all right, we get that frequency. That's 100 seconds, absolute ejection mass. It's up in the Planck spring constant regime. Okay. So that would mean, all right, so cool. All right, so we don't need all of that data. We only, I mean, H bar's only got 10 digits. That's more than 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. Okay. So let's do this. Okay, derivative of electron volts. Blah, blah. Okay. Okay, so let's, how are you gonna 3D plot? That's just a box. Number of significant digits. Where was that? Okay, well let's just give it an output. Squeeze a light squared. Okay. I don't want all those extra digits though. I don't know, let's do this. So since we only have 4 significant digits, let's just put in 4 significant digits. Times 10 to the, all right. Joule volts divided by joule seconds. There we go. All right, full from alpha results. Okay, per second. There we go. All right, format pod. And then we give us a frequency. I'm wondering what the log of that frequency is. I don't know. I don't know. I see a big number. I'm curious. All right, so a ginormous number of hertz. All right. I'm just curious. Oh wow, that's a really big number for a log. Okay. Yeah, I have no idea what any of that stuff is. Not even gonna try to pretend. Yeah. I mean, good luck. Okay. I was just curious. Where are we at? Okay. Oh, hello, Ray. Oh, why, thank you. Don't go cry. I am back in the greater Boston area. I'm busy through like next week, but I'm happy to go out with you and the dude to do some karaoke. All right. Yes, Dan. After reading NKS soon, not the same anymore. To be fair, there seems to be a general thing. A lot of folks literally took them like at least a year or so to read it. It's a very big book. Welcome back, Bill. Yes. Okay, yes. I'm trying to actually communicate things. Yes. Hey, welcome back, Rick. Excellent. All right, we got a good crowd here, so let's go through. I'm literally just setting stuff equal to things. That's literally what we're doing right now, to try to make some notation a little bit easier. All right, so, okay, I think we've got enough of that. Specific code. All right, we set our units to that. All right. Okay, so you go upstairs. 9 per second, the conversion, it's hertz. Okay, so we've got that elementary frequency, so to speak. Okay, I have to check one other thing. I'm sorry. I'm so scatterbrained. Hertz. H bar. Well, that is interesting. That's a lot of mass. That's, I don't know, 5 to 7 magnitudes of the mass of the estimated mass of the observable universe. Okay, now is it h bar? Or is it h bar times 2 pi? I think it's h. Yeah. These numbers look a little familiar. I don't know. Can't quite nail it. That I know I got one of those results before for something. I can't say. Oh. Frequency times h would be energy. Okay. All right. Sorry. Okay, so we got this. All right, so our elementary time. Okay, we should be able to express it a couple of ways. Okay, so I should probably just do 1 over t right now. All right, so 1 over elementary time. There we go. Give it a space. Oh, did I exit out? Did I not set this? Do I need to do that every time? That's kind of annoying. It's because it's not bold. I think it's because it's not bold. Is that literally why? That'll be kind of interesting. All right. Oh, I'm in the wrong thing, I think. Oh, display formula. That's why. All right. Evaluate. Put. There we go. All right. So, and over that dude. Yep. All right. Boom. There we go. All right. I'm sorry, I'm so simple. I'm just like, just give me the thingy. Alright. Will it be better if I do? I just don't want all those. Those digits are just completely made up. That's the problem with there. All right, so okay, so let's just do this. We have this. Boom. God, so bad. All right, so 1 over that. Yep. Okay. So we've got that one. All right. You can tell it's late when you see Professor Wolfram leaving the building. It's past 10 o'clock, so it's time to, I think, do social hour. Let's see, where are we? All right. Get that guy, get that guy. All right, so 1 over t gives us, I mean, it's literally going to give us the same thing. Okay, so, format pod. All these, oh God, I'm going to have to bother so many people to help me clean this up tomorrow. It's okay, at least we seem to be making some progress. All right. Okay, that was a student meeting. It's, I believe, or maybe it was just a Dr. Stephen Wolfram thingy. I filled out one of those for the very end of the program because it's not directly related, but may end up being related to the physics project. So, all right, I got you go there. Okay. Didn't we just do this? I think we just did this. Somehow I don't think I did anything new. Where did that other thingy come from? Oh, we did the, okay, calculations. All right. That's right. Okay. So we've got that, or... Oh, nope, not there. No. Copy cell. Or we may express the maximal entanglement speed notated by or we may express the maximal entanglement speed zeta as, all right, so okay, and then we just take our elementary. Okay, so it gives us that, or see zeta as zeta in regards to the associated energy with edges in the causal graph. Oh my God, it's so close. I'm just like, huh, how did he know? Okay, so zeta would be our let me do the formula thingy. Can I input my formula? I'm literally doing such a lazy thing, God. I'm so not qualified to be in a programming summer school. Alright. I'm literally just stealing these things. Oh, God. I'll just have to link to this page. Alright. So 1 over t as, okay. Let's see, this guy here. Oh, insert. File. I feel like some people might be trying to reach out to me to go out to Boston tonight, so, all right. Okay, I can make that a little bit smaller. Okay. And then get that guy there. Okay, and then we'll get this dude here. Insert from file. Be that. No, that was the same thing. Format. Nope. Insert. There we go. You can do it. Do the long one now. There we go. All right. You may even make that a little bit bigger. All right. Causal graph. And that's defined as elementary energy divided by elementary time, which will give us power. As elementary energy divided by elementary time. Okay, so now we literally just take, oh, we should just be able to take our expression. So, all right. Let's see if this works now. Okay. Appears to be working. God, that's crazy. Oh, God. All right. Okay, since we're only putting in 4 digits of input, should probably. All right, so, all right, so we got 4 digits of input. So that's all we really have. Divided by seconds. Seconds. All right. Go, Wolfram Alpha. Give me all those delicious results, my friends. Okay. There we go. I mean, I could just associate that, but I mean, for me, it's for an observer or a computer like me, it's like, oh God, I just call myself a computer because I'm doing computation stuff. Okay. Pod. It's got pretty dang good agreement. Oh my God, this might explain a lot. Wow. Okay. Wait a second. Oh my God. Okay. Pardon me. I'm sorry. I need to take this in for a second because. Okay, so long story short, I did some crazy calculations. I came up to a Planck Power. I don't even remember how I got to it. I'm like, what would this happen in Thad's model? My only thing was, I'm like, if you were to generate, what sort of dynamics would you need to power something like quote unquote universe? And again, this is massive speculation to a whole other magnitude of like, all right, so hypothetically, if we were to think that maybe universe could be represented by a Turing machine because hence universal computation, what would you need to power it? Planck power? I don't know. But I mean that's just ridiculous speculation. So to have evidence for that, you would need something extraordinarily compelling. And again, rampant speculation. Don't take what I'm saying seriously. All right. Got all that. All right. So our maximum entanglement speed be expressed as this. Our result is this. And it appears to be, at least according to these calculations, have pretty good agreement with the Planck power. Planck powers. Oh. Huh. So at least according to the Wolfram model, it looks like the maximum entanglement speed is the Planck power. Don't that just beat all? It's, let's see, where are we? Uh-oh, I apologize, Nolan. It's okay, you helped launch this quest for me. Oh, the exercise of principles of computational equivalence? Well, I guess maybe, well, if I can compute and a rocket can compute, then our computers can compute, and I feel like there's a little limerick I could make there, but I don't have the computational bandwidth right now. Oh. It's like 100 1-kilometer black holes. See, you're getting reference frames from other people. That's why this is important. Universe makes progress every day. Gotta buy coffee. Yeah, I gotta buy coffee. Go down to the little thingy. Well, see, this is the weird thing, because the maximum entanglement speed, it's basically just, it's 1 over the elementary time. It's a frequency. So rather than saying about 10 to the minus 90 or 10 to the 99 hertz or something like that, you could express it as this. Because, see, this is the bizarre thing. It's, how did he know? I don't even know. It's just the intuition. It's like, we're expressing this as this. I had looked at this before. I'm like, I'm pretty sure that's of the magnitude of the Planck power. And if we take the Planck flux, and again, maybe this shouldn't be surprising at all, but it just... And again, I don't know. Again, maybe just some numerology, but again, I'm of the opinion that numerology is numerology until it explains more with less. Maybe it does, maybe it doesn't. But yeah, if literally when okay, so 2 of the terms within the Wolfram Physics Project looks like it may literally be the dimension, like, it looks like capital psi is literally the magnitude of Planck flux, and zeta, the maximum entanglement speed in regards to associate edges of the causal graph as the Planck power. Huh. Okay, see, for me, a lot of the methodology and everything, I'm like, okay, this project has potential to do things, and now it's like, if we're literally finding the limits of the Wolfram Physics Project to be the limits of Planckian boundaries, I believe the term is, that's increasing my Bayesian priors in regards to as we go on, aka level of confidence is, it's ticking upwards. This is fascinating. Okay. Well, that's one of those things, though. Distance time relations. It's like, because that's actually how this was calculated. They're basically off like I think it's like the Hubble time divided by the Planck time. They're basically computing out, but oh, huh. Okay, that makes sense. No, it's linked by the speed of light, and I think we have 10 to the 91-ish meters, 10 to the 92. Yeah. Okay, that makes sense. Yep. Okay, so Bill's right. Okay. So let's note our progress file. Save. And note this again. I just happen to have a number that basically Xerxes was like, here's some advice. Follow the advice literally. Oh, I get a number. Professor Wolfram's like, you should really do some extra reading. I would recommend these sections. Okay, do some additional reading. Huh. When if I take it literally from a philosophical perspective, it's like, all right, you're looking for flux. This is the dimension of flux. This number seems to be of magnitude here. I actually thought it was far too small. Seems to be within 1 order of magnitude, and we seem to be getting out Planckian boundaries. Again, I ain't no genius or anything. I'm literally might just be the luckiest son of a gun. Like, literally, the only reason I am sitting here right now is because while I was trolling Professors Keating and Wolfram, Nolan trolled me. He tagged that. I just mouse over. I'm like, oh, I like that stuff. Click. Just by happenstance, I opened up Twitter on the day right before the Mu1G2 results. That was just happened to be premiering a video. I go in like 12 minutes in. I'm like, just because it was within my head, it's like, oh, I don't know if you covered this. Does this help your model? Yes. go back, look at that stuff, and then basically, yeah, history. I'm going through and I'm like, yes, Nolan, you are literally the only reason I'm here right now. Within the tangled causal web of our realm of persistence. You can't make this stuff up, man. I don't know. Maybe this is all made up. Maybe we're an anti-realist. And then I think Professor Barondus at that point's like, well, that's fine. You're not weirdo. We don't need to listen to you. His mind works in a very South Park / Cartoon Network type of way. That's probably also one of the reasons I kind of like him. So, all right. What happens to hypergraph depth? Oh. Well, see, Bill, I think that essentially the fringe of the graph, the edges of the graph are the quote-unquote defined cosmic horizon. I mean, there may very well be a limit to it. And again, if I'm going by this, it seems to infer that there is a limit, which would seem to be the connections between the nodes and everything. And that's why I'm like, all right, the general thought of you're going to have all these light cones or spheres of the observer particles or whatnot there. I'm thinking if you had enough, you might be able to lay a mesh down or something like that and basically have these graph type transformations. That's my gut feeling. I don't know. And again, I'm not an expert enough about these models. I can click on some code. I can change some rules. I can be like, oh, look, something cool happens. Again, the two most knowledgeable people in the world about this is Jonathan Garrod and Professor Stephen Wolfram. I think Jonathan just got married recently and stuff, and I emailed him in years. I sent him an email from, oh God, which, I don't even know, maybe a Gmail account to his new, I think he's over at Princeton now, maybe. Yeah, I just asked him for some tips on units, and I sat down with Professor Wolfram, gave some advice, and here's where we're at right now. Okay, so, all right, let's see. Yeah. Well, you need to take off Wolfram out again. It will fill in. It was because I think H bar had 10 digits there, so it's just filling in with zeros and stuff. Just we want to be accurate. Okay, so. Oh, wait, no, I need to get the cell. That's right, all right. All right, let's see. It appears that the maximum entanglement speed expressed in terms of the associated energy with it appears that the maximum entangled speed was expressed in terms of the associate. I'm just going to write it like they have it. It seems better to quote in terms of expressed in terms of the associated the energy. I'm sorry, I can't write it clearer than that. Associated with edges in the causal graph. In terms of the I'm just going to list that as a quote. It appears that the maximum entangled speed, when expressed in terms of the energy associated with edges in the causal graph, is the Planck power. What else do I say? That's the only thing that means meaningful. We've reached the number one. We have the one of flux. We have the one of power. And they were right within the ballpark within the estimates, and the deviation is really about half a magnitude. It seems to be about the same. Oh my god. How does he do it? How does he do it? Ah! See, the terrifying thing is slowly getting kind of a little bit more confident in this, because a lot of times it's like you go through thousands of Wolfram holes up and down, looking all around here, and it's like I've said a bunch of words, I've speculated wildly, and then you go through things and you get a calculation, and you're like, that can't be anything. And that's like, okay, you're sitting there, and I'm like, this seems to actually kind of be making sense. Oh my god, I did not expect this to happen. I'm just like, I thought it was just a completely different model, but well, if I'm gonna believe the word, my own BS, the words coming out of my own mouth, I guess we would expect this to happen, because if there's different ways to slice this and try to calculate what might be going on, and there's different ways to go about it, you would expect to run into interesting things. So it's kind of like, I don't know, a pure speculation thing is, what is it? Yeah, the inverse of the Z boson, inappropriate units, appropriate units. So you have to do kilograms squared. It's approximately the mass of Earth. That's kind of a crazy thing. I think a much less crazy thing is when, was it, Bill is doing the energy computation. At the surface of Earth seems to be about at least the energy magnitude range of h bar. I'm like, that is very interesting. Now, I'm going to have to save that for future work. I'm already so far behind. I should already be just doing my little picture, have my full write-up on the history of units done. Oh, God, I'm such a problem child. Expressed in terms of the energy, it appears that the maximum entangled speed, when expressed in terms of the energy associated with edges in the causal graph, is the Planck power. Wow. Okay, how long have we been going? All right, so we've been going for about an hour. Rick, I think Rick nailed it right there. We are all looking at the same thing. Different lenses, but the one thing that I've noticed is when I talk to a whole bunch of different folks far smarter than I am, I learn things, and then I kind of look there, and maybe it's just because I have the mind of a child. I may or may not have been dropped on my head as a kid, so it's excuses. But not just looking for potential tentative connections. And one of the things that Dad taught me is, what if I assumed it was right? I know Rick has given presentation on this too. It's like, there's no way that could be true. However, what if we were to assume it was true? Where might that lead us? And that one thing, that one trick may make all the difference. Because we might not have perfect information, but I think the goal is to be more perfect. At least that's what I've heard. Oh God, Bill, it might be interesting if when the causal node crosses an event horizon that adds oh my God. Yes. Yeah. See, that's what I was kind of thinking. Because your explanation, okay. We're gonna have to talk in the next few weeks then, just because I need to crank this stuff out literally by Wednesday night. So this is literally my crunch time right now. I say this as I'm talking with you, procrastinating, but I'm just always learning more stuff. Like it says, okay. Oh, there's a lot of this and that, and it's just you got a thing, you got the inverse of a thing. Yeah, I mean that. I'm pretty. Isn't that like the Sherlock Holmes principle? You just keep on investigating and investigating, and if you run across something so absurd, it's like, have we ruled everything else out? It's like, well, sometimes it's the craziest thing. Occasionally, maybe it's, who knows? Maybe Occam's razor. All right, great. All right, so the Planck Power. Well, it's at least answering some questions that I've had about things. It's like, minimum length and minimum time. Give us some maximum speed. Okay, that seems to be kind of straightforward, even though we can't directly measure light for some magical reason. So we have to do the two-way. I'm sure that's not telling us anything interesting. Um, okay, save. Let me just check. See what some folks are saying. Maybe folks already went out to Boston. Let me just check the schedule here. Oh, people are talking. I'm in the bubble. Oh, people are asking if we're going out to the club or for different activities. I don't know. Again, it's not necessary being not 20 years old anymore. It's like, okay, yes, that does take a toll, and it's probably smarter for me to just stay in. I'm not saying I'm going to do that, and I'm smart like that, but I have to at least say the words. Okay. So what else do we have here? Specific models. Okay. Well, it is. I'm gonna have to get there some other time. Okay. Okay. The structure of a model applies to not only length, time, and energy models. All the quantities indicate the mass electron is about. It's a quantized unit of mass, far too large. Let's see. Numerological relations between particle masses, but with our model of particles as localized structures and okay. Oligons. Okay, so let me just, for my own knowledge. Wait a second. Huh. Went over that. Okay, so that's where. Okay, so that the general estimate for that is, I believe, this. So let's just do this. Okay, so 1 over that gives you the 10 to the 61. All right, so let's do this. So if that's assumed to be 1, and that's 10 to the 61. You divide by the square root. Solve for x. Because if k is small, okay, it's going to give you a 1. Of course it is. Because 1 raised to something is 1. All right. Oh, equals x. I'm so dumb. I think we need to do that. Okay, now we'll give us some answer. Okay, yeah, it's just because your 1 is, yeah. Okay, what do we have? 1 point, I think it was 8. All right. So Yeah, that changes it when you do that. So, let's see. Okay, I think that's about all for now. Just because I'm drinking all this coffee, it's basically putting me under a little bit of pressure. So let's save one more time. All right, save as Wolfram flux 7 5 25 3. Save. Save as. Nope, save the cloud. Okay, I should also probably get out of here because one of the, I think, maintenance staff was giving me an eye. I want to clean out. It's 15 minutes before they close, so I should get the heck out of here. All right, save and file, publish. The cloud. All right, publish. All right. Cool. All right, everybody. So this has been fun. And again, this is just speculation. Statistically, this is probably nothing. If it's more than nothing, then, well, the Wolfram Physics Project may or may not be getting much more physically grounded, so to speak, and I don't know, shall we figure out the one rule that rules them all, or is the basis of our ontological framework? Who knows? Does something exist? Maybe it does, maybe it doesn't. Maybe someone watching right now or temporally in the future has the answer. So I guess only time will tell. So other than that, hey, thank you all for watching. Peace out, everybody. It's a crazy world out there, but here's hoping for a better tomorrow. I'll catch you all later. Peace.